Hello and welcome back to our image and video processing class. In the previous video, we saw in real-time histogram equalization. We saw how it improves the image and how we managed to get a non-uniform histogram and make it a uniform histogram. So let's see in detail how we do that. I'm going to show you exactly the math behind that, and you will see how simple it is. You will be able to go right away and program that in your own computer if you wish to do so. So let's just dive into it. So first of all, let's just go again and talk about histograms. Here we see a very dark image, and here we see the histogram. As we see, most of the distribution of the pixels values are in the low end of the histogram. There's not a lot of bright values, and we see that the histogram basically there, the count of pixels there is very, very low. Here we see the other way around, a very bright image, and most of the count is in the high part of the histogram. So there's not a lot of pixels with low values. Here we see kind of a gray, low contrast image, and then we see that the pixels are actually concentrated in the middle. While here we see an image that looks much nicer. These are all the same images, but this looks much nicer. And we have kind of a uniform distribution. We are occupying the whole space of pixel values, more or less uniformly, and then the image looks much, much nicer. So we want to be able to learn how to go from a distribution like this to a distribution like this. And again, as I say, it's a very, very simple operation, as we're going to see in just a minute. So our goal is to go from a given distribution to a uniform distribution, assuming that our pixel values can go from 0 to L minus 1. For example, standard L is 256, so we can go from 0 dark to 255 very bright or white. And we want to get a uniform distribution. So basically the probability, or if we don't normalize the count, but let's just think normalize is just easier, the probability is 1 over L minus 1. That's basically the probability of having a pixel achieve that gray value. So we want to go from this to this. That's basically our goal. In order to achieve that, what we need is to find a transform that takes basically the pixel values of the original image and transforms them to pixel values of a different image. So having an image, I need basically to decide for every pixel in the image, I want to see its value and I want to transform it to exactly the same place but with a new value. And remember, so far, we're only making decisions based on the pixel value, not on the neighborhood, just on the value. If the value is 7, we need to decide what we transform 7 to, regardless of what are the pixel values around it. So we need a transform that takes us from any pixel value to a new pixel value in such a way that we get a uniform distribution. There's going to be one requirement of this transform, and we're going to make an increasing transform. And the reason is we don't want to reverse pixel values. So we want this to be a monotonic increasing transform. If 7 goes to 10, 8 should go to a value at least 10, maybe above 10, but we don't want 8 to go below 10. And then we actually kind of flip the content of the image, and that's not the intention of histogram equalization. So we're going to have increasing functions, and finding this function is our goal. Now, sometimes we have strictly monotonic increasing functions that every pixel value goes to a different pixel value. Sometimes we have an increasing function is monotonic, but some of the pixel value might end up with the same target. And we will see that that will happen in histogram equalization, in particular when we work with discrete images and discrete pixel values. So we are going to end up with a transform of this style and not a transform of this style. That's basically a problem with histogram equalization in discrete computers, but it's something that we must have, we cannot avoid, as we're going to see next. So how do we achieve this? The basic idea is very simple. We can think about an histogram as basically a distribution S. So this is where you need a little bit of background in probability, but don't worry, because even if you don't have that background, I think it's going to be almost self-explanatory what I show next. So we have a distribution. The histogram is nothing else than a distribution. What's the probability of a given pixel value? We want to obtain a new one. We actually have the current one. So basically we have a different distribution. And remember, what we are looking is for a map from R to S. We're looking for this transform. So it turns out this is a basic result of probability, that if we have such a map, then the relationship between these two distributions is as follows. This is the relationship. So the new probability distribution is the old probability distribution times the absolute value of this derivative. That's a well-known result from probability distributions, and it's all what you need to understand the rest of the derivation. So let's just assume for a second, and I'm going to prove you that this is the transform that we are looking for. Let's assume for a second that this is my transform. So S is a transform. So from any pixel value, I will get a new pixel value. And let's write it as L minus 1 times the integral from 0 to R. And I'm going to explain the interpretation of what I'm writing in a second, of the current histogram or current probability distribution PW dW. So what am I doing here? I'm basically integrating the mass, the number of pixels that achieve a given gray value from 0 to R. And then I'm doing this because I'm using probability functions, so I'm normalized between 0 and 1, and I want to get back gray values. So let's look again at the transform. You count, if we are in a discrete space, you're going to count, if you want to know to which pixel value should I transform the value R equals 7, you count how many pixels are at 0, how many at 1, at 2, and 3, and so on until 7, and that gives you the transform. I have to prove to you that this is the right transform to do histogram equalization. So let us do that. In order to do that, I'm going to compute this derivative. And the basic idea is very simple. So we're going to actually do ds dr. Now we have the explicit transform here. So we can compute this derivative. Is basically d of dr, and we have here the expression. So it's the derivative according to R of this expression that we have here, L minus 1 times the integral from 0 to R PR W dW. I apologize that the rows are going one on top of the other, but I think it's very clear. So we need to compute this derivative. And if you remember basic calculus, this is a constant, so it will go out, okay? And then the derivative of this integral is what's inside the integral. So this is equal to L minus 1 times, and I'm going to write this here in the next line, P R R. So we obtain that the derivative of S according to R is L minus 1 times the probability, basically the original histogram. Now what we are going to do, I'm going to erase this in a second, but what we are going to do is basically include this here and see what happens. So I'm going to plug this in here, but look what we have here. We have dr, ds, and I have here ds, dr. So we need to invert that. It would be 1 over this. And I hope that you can see what's going to happen. So let's see actually what's going to happen. Again, we have P. The new probability that we are looking is the old probability dr ds, absolute value. We computed the RDS just a second ago. So this is PR R, the absolute value of 1 over L minus 1. That was our normalization, P R R. Now, probabilities are positive, and this is positive, certainly positive, because L is greater than 1. So I can get rid of the absolute value, and then I see that this will basically cancel with this, and I got 1 over L minus 1. And that's exactly what I wanted. Exactly what I wanted is to have a uniform, a constant probability distribution for my new image. Okay? So once again, I'm going to write again what's actually the actual transform. S, which is a map of R, is L minus 1, the integral from 0 to R of the original probability distribution function, or histogram. So it's a very simple function. You go and you count how many pixels have a value up to R, and that's your transform. Very, very simple operation. It's basically a one-line code in almost any programming language, and that will achieve us histogram equalization. So let's see this in action. First, let's just take basically an artificial example where we have 8 different values here. This is the counting. So we have 790 pixels that have value 0, and 1023 pixels that have value 1, and so on. And we just transform this into a probability because we have been working with probabilities, and this is the probability that we are going to get. We plug that into the formula that I just showed you, and this is what we are going to get. So first of all, this is the original histogram, PR. This is the distribution that we have. If you plug that into the formula we just showed, this is going to be the transform. No, it's going to be monotonic, and we know that because we are integrating. Let me just write that again. The basic operation was to integrate from 0 to R. So the more I integrate, because what I have in here is positive, it's clearly an increasing function. I'm only adding more and more positive numbers, so it has to be positive. So it's an increasing function, and what it tells me that 0 goes to this number, 1 goes to this number, and so on. So it becomes a very, very simple map. And this is going to be the new histogram. Now you may wonder, it looks more uniform. And one of the things that happens, because we are working with discrete data, we're working with images in the computer, we're going to have to round numbers. So for example, the 4.2 will become 4. So we end up actually with less peaks than we had here, because these ones at the end will merge into the same integer number. And that's the price we pay for working with discrete images. We cannot represent 6.7 and 6.8. Will both become, although the formula tells us they should go to different numbers, they will both become, let's say, 7. In a similar fashion, let me ask the following question, which I'm going to ask you to think for a second and then respond to me. Let's just look at an histogram that has the following form. It has only 2 different pixel values. These 2. Doesn't matter what exactly are the values here, but this is the original distribution of pixel values. There are only 2 values in the image. This is a binary image with only 2 different colors, 2 different pixel values. And I'm going to ask you, what's the relationship between the map for a pixel value here and a pixel value here? So let's just call this A, let's just call this B, and I'm asking you the relationship between TA and TB. Are they equal? Are they different? Is TA greater than TB? Is TA less than TB? So just think for a second and give me your answer, and I'm going to come back right away and give you the explanation for the correct answer. So let's look at what is the correct answer. Remember, what we are doing in histogram equalization is we are integrating, okay? So I ask you, what's the relationship between these two? Are equal, less, or greater? We know, first of all, that TB should be greater or equal than TA because we have a monotonically increasing function. But let's just look a bit more in detail what happened. This actually is going to integrate the whole mass up to here. So basically it's going to integrate only this. Here it's going to integrate everything up to B. But there's no new mass between A and B. Since there is no new mass, then what happens is that TA will be equal to TB. And as an extra exercise, you can think about what's going to be actually the transform for this one and what's going to be the transform for this particular one. And it's basically related to the average on the image. Just do that as an exercise on the side. But this is very important illustration that basically the transform that we are looking for, even before we have to round or quantize because we're working with discrete images, even before that, is not strictly monotonic. There might be more than one values that end up with the same transform. You can, of course, say, we don't really care too much about that because in the original image, there were no pixels with initial gray value A. And that's correct. But I want to show this both to illustrate that the transform does not have to be monotonically, strictly monotonically increasing. It has to be monotonically increasing, but not strictly. And also to illustrate once again that all what histogram equalization is doing is basically counting the number of pixels up to the value that you want to map. So I'm counting the number of pixels up to A, and then the number of pixels up to B. So after this exercise, let's just see a few additional examples. We, of course, saw examples with the online demo, but let's just illustrate one more example, which I think is very useful. I'm going back to the images that we started. This was dark. This is what's happening after histogram equalization, and the histogram looks much nicer than before. So let's just look at the map. This is the map. Pixels value from here get mapped to here. Okay? So this is my R, and this is my S. And look at the map. The map basically it has a very, very high slope because it's trying to very fast map very dark pixels to brighter pixels. So it has a very, very sharp slope. Let's look, for example, at this one. This one was pretty good to start from. It hasn't changed a lot. And actually, this is the map. It's almost a unit slope, a map in the diagonal. There's almost no changes in the pixel values. And similar interpretations for the other two maps. This one actually needs to darken the pixels, and we see that in the corresponding map, that basically look what happens here. And this one needed to stretch the pixels. Remember, they were in the middle. It needs to stretch them, and we actually observe that here. It's basically stretching the pixels from the middle. They were all around here to start from, and it's going to stretch them, and we see that it actually occupies the whole range from this, which was the very big, very narrow band that it occupies the original histogram with very low contrast. It's actually mapped now to the whole spectrum from 0 to 255, and we see that in the map as well. And of course, we end up with images that are very similar regardless of where we started, because these images actually were created from these images, from an original, let's say this one, just by changing the contrast. And then after we equalize them, they look much closer. And that's a technique that is used very often to make images that were taken under different conditions look much more similar. We equalize the histogram at the same time we're making the images look much more similar, and then we can compare between them in a much more friendly fashion. So this is basically histogram equalization. What we are going to do next in the next video is histogram transform. What happens if I don't want to equalize an histogram? I want to transform it to an histogram that I know is going to be very good for my image. We're going to see that in the next very short video. That is also a very, very simple operation. Thank you.